Okay, so number 10, they want us to pick which type of radioactive decay will result in a product with a greater atomic number than the original isotope. So I've written out here the three types of decay that we usually think of, where we have alpha decay, which is the emission of a helium nucleus. We have beta decay, and then we have positron emission. Okay. So hopefully you can see how when you're emitting an alpha particle, like I've written here, because the lower number corresponds to the number of protons, as we shoot off these particles, our atomic number would go down by 2 for each particle. Okay. So elements with an atomic number greater than 83 do this because it's a very efficient way to get rid of matter. Okay. This beta emission, though, is actually the opposite, because to balance the right and left, so if we had some element like neon, we could have neon, which has neon 20, which has 10 protons. If it underwent this, oops, wrote that in the wrong spot. If it underwent this beta emission, to balance the left side of the reaction with the right side of the reaction, we would actually have to increase our number of protons there. And so this would now be sodium. So we've increased the atomic number through beta emission. Whereas if we did positron emission, we would decrease the atomic number to 9 to balance between both sides and become fluorine. Okay, so the answer to this question is just beta decay. And we tend to do beta decay when we have too many neutrons. Question number 11 is asking us which of the following species is the strongest reducing agent. So I went ahead and wrote there that the reducing agent is what gets oxidized. So we want to pick which one is just best at being oxidized here. So we can think about going ahead and writing the reactions. Okay, so there are the reactions, the half reactions for the oxidations of those things. So I've just taken the species given to us on the left and written them as if they'd lost an electron. And so if we consult our table of potentials, we can see how favorable these things are, because we know an increased E is better, more favorable. So here we have the reaction of lithium plus losing an electron to form Li2+. Hopefully you guys can see that this isn't going to happen. That doesn't make sense. Lithium can't lose 2 electrons. Okay? It's much more likely to be reduced. Okay, so this doesn't make sense. No. And the same goes for Br2. We don't really see Br plus around, we see Br minus. Okay, so this reaction also won't happen. The bottom 3 all will happen, and you can find them on the data sheet and look at their standard potentials. And because I'm writing them for oxidation, I'm going to flip the signs. For the iron, well, negative 0.771 volts. For the chlorine, we'll have negative 1.359 volts. And for nickel, positive 0.28 volts. Okay, so the nickel value here for the oxidation is most positive, which kind of makes sense too. Metals like having positive charges. So then the answer here is E. So make sure you can use that table to figure out the oxidation potentials. Okay, number 12, we have another figure out what the KEQ problem is. Here they've given us two formation constants for these complexes and an overall reaction with the complexes. So to the right of each of those, I wrote the expression that would describe what's going on, because KFs always describe the formation of your complex. Okay, so I just took the inner components of the complex and added them together. And then we want to see how we can relate these two equations to make this top one. Okay. So hopefully it's kind of obvious to you guys that to make this top expression, we would have to flip our first one. Okay, so then if we flipped it, we would have the overall reaction from above. Okay, and so if we're going to flip a reaction, we do 1 over the K. So I'm going to circle this one in pink so you know that that's the K I'm referring to, the pink K. And then to combine KEQs, we multiply them together. So I'll make this one the green K. So this will give us our overall KEQ. So really, what we'll have here is just 6.8 times 10 to the 17th divided by 1.2 times 10 to the 9th. Okay, and so that ends up being answer choice B, which is 5.66 times 10 to the 8th. Okay, so again, a big K, any K greater than 1 is going to be products favored. For number 13, they're asking us to figure out which reactions will occur spontaneously in standard conditions. And hopefully you can look and see that these are all redox reactions. Okay, the charges on different metals are changing. And so to answer this question, what we really need to do is see if the overall E will be positive, because a positive E is spontaneous. And so we can split them into half reactions. I've done this for the first set, for the first equation, where I have the oxidation of iron half reaction and the reduction of aluminum half reaction. And from the table, I got the E naught, or the half potentials. And so we would go ahead and just combine them and see that this will have an overall potential of negative 1.22 volts. Okay, so that's negative. That's not spontaneous. Okay, so the first one is out. And so we would just go through and do this for each reaction. So I've gone ahead and written the half reactions, again for that second reaction between silver and tin, where we have silver being reduced and tin being oxidized, and I used the table to get the values. So now I'm just going to combine them to get my overall potential. We get positive 645 volts. So this is positive, so it is positively spontaneous. Okay, and we can continue on this road to do it for the reaction with hydrogen and then the reaction with iodine. Okay, so looking at the half reactions for the third set, we get the potentials from the table, and we see hydrogen 0, which makes sense because everything's centered around that being 0. And then we get the nickel value. And so you can see that the cell potential is going to be negative 0.28 volts. So this one is also not spontaneous. So finally we have the half reactions for the reaction with iodine and chloride. So I've written the half reactions and used the table to get the values. And now if we were to add these together, we would get negative 1. We would get a negative potential. And so that negative potential makes this one also non-spontaneous. And so B is the answer because it's only the second reaction that's spontaneous. And so spontaneous reactions we usually put in voltaic or galvanic cells. Okay, so if you're ever not sure how to start these problems, just write the half reactions, and they can hopefully be a guide for you. So 14 is asking about molecular orbitals, and which of the following diagrams give us bonding molecular orbitals. Okay, so we know that bonding orbitals are when we have overlap, whereas with antibonding orbitals we have nodes, which are areas where electrons can't exist. And so we can see here we have that overlap. Okay, so this would be bonding. Whereas in the second picture, this area where the electrons can't go is a node, so this would be an antibonding. 3, for the same reason as the first one, is bonding, so we get the overlap. And 4, for the same reason, that would be an antibonding orbital. Okay, so this is B. For number 15, it says that it takes 200 seconds for a first order reaction to go 25% of the way to completion. And then they're asking us to figure out what the half-life of the reaction is. So it's important to note that we're talking about a first order reaction because we'll use different equations for a first order and a second order reaction. So here I've written out the first order half-life equation, as well as the first order integrated rate law. So the connection between these two equations is K. So if we can find the K using the bottom equation, then we can plug it into the top equation to figure out what our half-life is. A tricky part about these problems is that when they say 25% of the way to completion, that means that we still have 75% left. And so we're actually going to work with that 75% instead of the 25%. So we can rearrange this first equation to get that the ln of A over A naught is equal to negative KT. And that A over A naught is going to be equal to the 75%, because we're saying we still have 75 of our initial 100%. So go ahead and do ln of 0.75 is equal to negative kt, and they say in the problem that t is 200 seconds. So just dividing over, we find that k is equal to 0.0014 seconds. And so that will be our connection into the half-life equation. We can go ahead and say, now that T1/2 is equal to 0.693 divided by 0.0014 seconds. And this ends up being 482 seconds, which does correspond to answer choice C. But it's important to remember that one thing that's unique to first order reactions is that the half-life doesn't depend on how much we're starting with, like it does for second order reactions. Problem 16 is asking us about HPO4 2- and what kind of species it is. And so we can take HPO4 2- and add it to water, and there are two possible things that can happen. Either it can deprotonate to form just the phosphate anion, and thus having donated a proton to form hydronium. And we would classify this as an acid, right, donating a proton. In the reaction below, we see that it can also steal a proton from water to generate H2PO4-. And so in that equation, it would be acting like a base. And when something acts like an acid and a base, we denote that species to be amphoteric. Amph meaning both. Okay, so this one's just C. So make sure you can write the acid reactions and the base hydrolysis reactions.